Hi, my name is Shahnawaz. In this lecture, we will study the arrow and slice categories. So we know if we are given a category, say A, so with this category we can create a new category using the dual notion, and we call that category the opposite or dual category of A. Similarly, if we are given two categories A and B, uh, then we construct a new category, and that is called the product of A and B. This is called the product category. So likewise, if we are given a category A, so we can create an arrow category from the given category. So we have this is the definition here. So this is the definition of arrow category. So suppose consider a category, say A. Let us call this category A. So suppose this category A has the object class OB, the arrow class say home, the identity 1, and the composition O. And with this category, we form a new category that is called the arrow category. And then uh, the arrow category, which we denote by category A with this arrow. So this category, uh, I mean the object class in category uh, A is the arrow class of this category A. So this is the category whose objects are the morphisms of category A. I mean the morphism class of this A. I mean the object class of this new category is the morphism class of A. I mean the homomorphisms in category A. So if we have two objects in this category, so if now keep in mind that the objects in this new category are arrows in the category A. So let us take two objects, say F1 or say F and F prime. So they are the new objects in the category A. So now these two elements F and F prime being the objects of this category, so then uh, since these two elements are the morphisms in given category A, so there must exist say objects A, B, and A prime, B prime, such that F is a morphism from A to B, and F prime is a morphism from A prime to B prime. So then there are objects say A, B, A prime, and B prime in the object class of A, such that F is an arrow, such that F is an arrow. I mean, this is arrow in the category A from object A to B, and this F prime is an arrow in the, I mean, arrow from the object A prime to B prime. Now, f and f prime being objects in this new category, so then there must be a morphism from f to f prime. So now let us exhibit an arrow between these two elements. So an arrow from f to f prime is actually a pair of maps. Is a pair, say G and G prime, or let us call this G and H. So of arrows in A, such that the following diagram commutes. So in the given category A, we have object A and object B, and between these two objects we have an arrow F. Similarly, we have object A prime and B prime, and between these two objects we have the morphism F prime. Now these F and F prime, they are the objects in the arrow category. So there must be an arrow which carries this object F to this new object F prime. So we call we we denote that arrow by a pair G and H, while G is an arrow between A to A prime and H is an arrow between B to B prime. So such that this diagram commutes. That is, uh, if we first go by the map F followed by H, that has to be the same map. First go via the arrow G followed by F prime. So this is the case with the objects. Now, as far as the identity morphisms on objects are concerned, so the identity arrow, say on object F, given by 1 sub F. So this identity arrow is on object F in the arrow category. So where this F is some arrow in the given category, say between objects A and B. So this is again a pair given by the identity on A and identity on B, such that the diagram commutes. So this is using the same definition as above. Here now we have the object A, we have the object B, and we are given an arrow F between these two objects. Similarly, we have object A and B in the given category A, and between these two objects we have a morphism F. Now this morphism F is our new object in the arrow category, so there must be an arrow which takes F to F, i.e. which is the identity map. So by this definition, we call that arrow to be the pair which takes A to A and B to B. Now A goes to A via the map identity on A, and B goes to B via the map identity on B. So since this diagram commutes, that means so which so so this gives this identity on A and identity on B. So this is actually the identity on, this is same as the identity on the object F. So this pair takes the morphism F to F using this definition. Now let us see how the composition works in this new category. So the composition of arrows in this arrow category is done component wise. So is component wise. So what do we mean by that? So that is, if say we have a morphism, say h1 h2 from the object, this is an arrow in the arrow category from object f to f prime, and we have an arrow say g1 and g2 in the arrow category from object f prime to f double prime. Then the composite map g1 g2 composite with h1 h2. So it is given via, it is given by the pair g1 composite with h1 and g2 composite with h2. So this map takes the arrow, this map is the arrow which carries the object f to f double prime. So let us see how. So we have object A here and we have object say B here, and between these two objects we have the map morphism F. And suppose we have the object A prime here and B prime. Let us call this morphism F prime. And suppose we have object A double prime and B double prime, and we have the morphism F double prime. Now we have to exhibit a morphism which carries this F to F prime, and that is a map, that is a pair H1 and H2. Similarly, the morphism which carries this F prime, so this is F prime to F double prime, is a map given by G1 and G2. Now so finally, the morphism which carries F to F double prime is this pair, this map and this map. This arrow is given by the map and G1 composite H1, and this is given by G2 composite H2. So since this diagram commutes, so that means G1 G2 which takes the morphism F1. So from this diagram, from this diagram, so one can see that the pair G1 G2, so it is an arrow which takes F prime to F double prime. So it is like this, which takes F prime to F double prime, and uh, the morphism, the arrow H1 H2, it carries the object in the arrow category. I mean, it carries the object f to f prime. So note that the composite map, uh, I mean the composite morphism G1 composite, G1 G2 composite H1 H2 carries the map f to f double prime. So this carries the object f to f double prime, and so does the morphism G1 composite H1. So the pair G1 composite H1 and G2 composite H2. So this again takes the morphism F. So this again takes the morphism, I mean the object F to F double prime. So hence they must be equal. So this was the arrow category. Now let us define the slice uh, category. So again we have a definition. So let us consider a category A. So let A be a category, and let us fix some object, say X, in the object class of A. So then the slice over X. So then the slice over X is the category given by A sub X. I mean A under X, A under X with. So here the object is in this category as well with the objects. So the object is in this category is a pair y comma f. So this is the object in this new category, where this f is a morphism from y to x, and a morphism a morphism say h in this new category, which takes the object say y1 f1 to the object y2 f2, is such that the diagram commutes. So we have two objectives, y1 y2. Since y1 f1 is the object in the slice category, so this f1 is a morphism from y1 to x. So this is f1. Similarly, y2 f2 being an object in the slice category, this f2 is a morphism from y2 to x. Now this h is a morphism which takes this object to this object. So this h is given like this. So then we call this h a morphism between these two objects if this diagram commutes. That is f2 composite with h is same as f1. So now if one wish to look at the identity morphism, I mean the identity morphism on an object, so that is given like this. So the identity morphism say the identity morphism. I mean one. So I mean the identity morphism on object, say, let us note by this by one of yf. So this is the identity morphism on object yf. So this is a morphism in the slice over category, which takes this object 1y, sorry, which takes the object yf to yf. So now if this is a morphism, so then that means this diagram commutes. So we have y here, we have y here, and we have x here, and this f is a morphism from y to x, and this is a morphism from y to x, and from y to y we say we have this morphism y1 yf. Now since this diagram commutes, that means this f1 f, so that is f composed with this map 1 sub yf is same as f. Similarly, one can define the composition here. So the composition goes like this. So, uh, so given, say, morphism phi from the object, say, so this is the morphism in the slice category from object y1 f1 to y2 f2, and another morphism says psi, which takes the object from the object y1, sorry, y2 f2 to y3 f3. So this morphism takes this object to this object. So then the composition is given such that the diagram commutes. So then the composition is given such that the diagram commutes. Now the diagram here is given like this. So we have a morphism from this object to this object. So here we have y1, y2, and here we have x. So we have a more an arrow f1 between these two objects, and here we have the morphism f2, and from y1 to y2 we have the map phi. Similarly, uh, we have a morphism from y2 f2 to y3 f3. So we have y3 here and an arrow which takes y3 to x via f3, and this psi is an arrow between these two objects. That means psi is a morphism between y2 and y3. Now since this is happening inside the slice category, that means this diagram commutes. That is, I mean, if we go via this way and this way, that is same. Now going via this way is, I mean, first you have to go via phi followed by psi and then followed by f3. So it is same as going. So this is a morphism which takes y1 to x. So this is same as going via this map, I mean f1. So the composition goes here like this. Now this is the case of slice over category. Now using the dual notion we can uh, define the slice under category. Now, slice under category is defined in the similar fashion but using the dual notion. So we have this definition. So let A be a category uh, and X be an object in the category A. Now the slice under X, the slice under X is the category is the category denoted by X under A with objects. So here the objects are like this y comma f. But now this f is a morphism which takes the object uh, x to y. So in the slice over category, this f was supposed to be an arrow from y to x, but in this case it is an arrow from x to y. And a morphism, say, let us call this phi, which takes the, suppose, now this is the morphism in this slice uh, under category. So this is in this category, which takes the object, say, y1f1 to y2 f2 is such that the diagram commutes. Now the diagram here is like this. So we have the object y1, y2. Since y1 f1 is an object, so we have an arrow f1 from x to y. So this is x here. We have an arrow like this. Similarly, since y2 f2 is an object, we have an arrow from x to y2, which is given by f2. And since this phi is a morphism from these two objects, so phi is supposed to be like this. Now this morphism is such that this diagram commutes. That is, f2 composite with phi is f1. So one can use, in similar fashion as we did in the slice over category. We defined the identity map there, the composition. So one can, uh, verify those things in this dual uh, notion of this category. Now we just want to define the constants. Now, so this is constants. So if we consider the category set, so in the category set, an element x of a set A. So if uh, A is an object in set A, then an element of a set X, set A is the image of a function from a singleton set to A that takes the unique element of the singleton to X. So, so what we are actually saying, so suppose we have some element X inside set A, then this X is determined by a function, and that function is from a singleton set, say the star, to A, which takes the star to X. So that means each element in A can be identified with a function from a singleton to X. So thus, if we pick a specific singleton, say star, and call it 1, Let us call this singleton 1. The elements of the set A are in one-to-one correspondence with the set home 1A. So let us first write this down. So in set A, an element, say x of a set A in this category A, is the image of a function from a singleton set to A, that takes the unique element of the singleton to X. So thus, uh, so if this singleton is denoted by, so if we call this singleton set, say star, so if we call this singleton 1, then the elements of A are in one-to-one correspondence with home 1A, which is a set of all functions from the terminal object to A. Moreover, if f is an arrow from object to A to B, so this is a set. Suppose this f is a set function, and x is an element of A, determining the function x from 1 to A, then the element fx of the object B is essentially the same thing as the composite. I mean, so moreover, if f is an arrow from A to B, so this is a set function, and x belongs to A is an element determining the function x from 1 to A. So then the I mean then the element f of x, which is an element of B, is same thing as, I mean, the composite, which is given by this map from 1 to B. Because of this, I mean, we sometimes uh, we sometimes call an element x in A being a constant x from 1 to A. So due to this reason, the categories typically typically thinks of an element, say x in A, as being the constant x from 1 to A. X from 1 to A. So an arrow from 1 to A in a category where 1 is the terminal object is called the constant of type A. Thus, each element of a set is a constant in the set. On the other hand, so let us first write this down. So we have a definition. So an arrow from the object 1 to A in a category A, while 1 is a terminal object, where 1 is the terminal object, is called a constant of type A. The more common name in the this literature for a constant is global element of a name that comes from sheaf theory. So the more common name for such a constant is global element. So global element is actually an arrow from 1 to A in a category where 1 is the terminal object in the category. Now we will use these global elements to generalize the notion of the injective maps to monomorphisms. So with the help of these global elements, we can prove that the in the category set the monomorphisms and the injective maps are same.